Hey, and welcome back. So, before we begin today, let me just mention two things. So, the first thing is that I'm aware of that I occasionally can make some small mistakes here and there. Now, it's unfortunate, of course, but sometimes I could say left instead of right when I mean right, or I could say 256 instead of 255, stuff like that. So it's unfortunate, but I talked to a guy who's a professor in London, and he also has two courses for programming in assembly language for the Atari 2600 and for the NES. So he has a lot of experience with this, and he said that unfortunately this is just one of those things where the brain is working overtime with a ton of details, and you need to explain everything. There are a bunch of numbers, and especially for us who need to use English as a second language, that's just an extra layer of complexity. So, unfortunately, the result of that is that sometimes there can be some minor mistakes here and there. Now, hopefully, that doesn't do too much damage. If you follow the course from beginning to end, it shouldn't do too much damage. But it's a little annoying, of course. But I just want you to know that I'm aware of it, and I'm going to try to do my best not to do those mistakes. But unfortunately, they might happen from time to time. Alright, so that was the first thing. The second thing is a book recommendation for learning assembly language. And that's this book. This is a fantastic book by the late Jim Butterfield. I have to say that for learning machine language and sort of assembly language at the same time, this is definitely the best book I have ever read. So it's a book from the 80s, but it's really, really good. So if you can get a hold of that, then definitely go for it. And if you can't get a physical copy, I think there's a copy at archive.org. Alright, so with those things out of the way, now let's get to today's episode. So once again, we are looking at the Commodore 64 memory. Now, we have looked at this quite a bit, so we're starting to get familiar with it. And we know that there are some ROMs here, and there are some free. There's a pretty big free memory. Sorry. There's a pretty big free area here in the memory. And we also know that when we start our program, we start at 0801 here. If we don't do anything, if we don't specify any memory addresses where we want to cram in stuff, then we just start here and we start filling up the space from here. So code, sprites, music, whatever. It's just gonna start here, it's gonna start filling up like that. Now, that is not a particularly good idea. So one of the reasons that's not such a good idea is that sprites and the character set, those two things need to be at some specified addresses. We need to know where those are, and the Commodore 64 need to know where they are. So as I said, if we just started doing things here at 0801 and started filling in whatever, code, sprites, music, character sets, whatever, then we wouldn't really know what memory address our character set was at if we didn't specify anything. Maybe we had a bunch of code. Maybe we had so much code that code tables, whatever, are levels. So maybe we got all the way up here before the character set began. And then the character set just began filling in here at a random position and going over here. So we can't do it that way. We need to be much more tidy. We need to do this in a controlled way. So especially things like the sprites and the character set, those need to have an exact memory address, both for us as developers, but also the Commodore 64 needs a specific memory address. So we need to plan how we're going to use our memory. How much space is this going to take? How much space is that going to take? How much space can I use for sprites, for example? So in those cases, we actually need to use our calculator. And we need to remember that one sprite is 64 bytes, for example. So how many sprites do I actually need? Maybe I want, let's say, 100 sprites. So I'm going to multiply this by 100 sprite graphics. So 100 sprite graphics, that's going to take up 6,400 bytes. In hexadecimal, that would be 1,900. So it's actually quite a lot. So if we started placing our sprites here at 2000, for example, if we started cramming sprites in from address 2000, and we know that it's 6,400 bytes, so 1,900 in hexadecimal. So if we add this number to 2000, then we actually go past what we talked about last time, starting our character set at 3,800. Excuse me. So if we are going to follow that plan, then this is going to collide with that. So I can't use that many sprites in this case. So how many sprites how many sprites can I use? Well, now we need to look at everything together. So, for example, I'm going to start filling in music from address 1000. Now, the reason that we don't want to fill in sprites here at address 1000 is because of the thing we talked about last time. So you remember this parallel universe down here. So there's actually a character RAM that the VIC chip can see down here. The CPU can't see it because at address 1000 the CPU sees the data in the normal RAM area, but the VIC chip can see this character RAM down here. So it's almost like you can store something beneath. Now let's not get into that. Anyway, the point is that this is what the VIC chip sees. So the VIC chip is going to see this character set, so we can't store any sprites there. Now if we store sprites here at address 2000, and that's gonna be perfectly fine for the VIC chip to read. So I don't want to go into detail because I noticed already that this can get super complicated. But as long as we remember that it's not a good idea to store sprites at address 1000 because the character RAM is there. So starting to cram sprite graphics at address 2000 is a much better idea because there's not any graphical data already there. So the VIC chip can read our graphics without any problem. Hopefully that makes sense. All right, so we can cram music in here. because or any code for that matter, because that's going to be read by the CPU. So that's not a problem. But cramming graphics that the VIC chip is going to read, that's not a good idea. It's not going to work. So I'm going to cram music data in here. So let's talk a little bit about music. So here I am in my application Sidplay, or not my application, but it's an application called Sidplay. So this is for the macOS. If you want it for Windows, I don't think you probably need to use something else. But anyway, this is an application to play Commodore 64 music, so-called SID files. So I asked permission from this great guy called Linus Åkesson. And he said that it was okay for us to use this file in this course. So shout out to Linus for letting us do that. It's really cool. So this is a SID file which I can play. So the Sidplay is an application to play those music files. And you can search for music from games or whatever. But there's also another great function in Sidplay. So if I, with my song selected here, I press Command and I on the Mac. Not sure what that would be on Windows, but anyway, now I get some information about this file. So this is important, and we're going to come back to that when we're talking about music later, because here's the starting address and so on. But in this case, the important thing for us is file size. So it says here it's 4,990 bytes. So 4,990 bytes. In hexadecimal, that would be 1,370E. So almost 1,400 in hexadecimal. So that means that I'm not going to be so specific that I'm going to cram everything byte to byte, just leaving a little room here and there with some free bytes is not such a bad idea. So I'm going to say that, alright, my music file is going to take up 1,400 in hexadecimal. So, because it's 4,990 bytes, right? So if I go back to my spreadsheet now, that means that now my music file is going to take up space from 1,000, and remember this. I'm going to say that it's 1,400 in hexadecimal. So 1,400 plus this starting address, which is 1,000. So I'm going to add 1,000 there, and now I end up with 2,400. That's going to be my starting address for the sprites. So the music starts here at 1,000 and it goes all the way to 2,400. That's where my sprite starts. So now I need to do some more math. So I just found out that this is the starting address for my sprites. Alright, let's think about this. This is the starting address for the sprites, 2,400. Now, we already know where we're going to place our character set. So, I said that I'm going to place my character set at address 3,800. Now, if I subtract the starting address for the sprites, which was 2400. So minus 2400. Then I end up with this 1400 in hexadecimal. So what's that in normal decimal? 5120. Alright, so let's just try to keep track of what we're doing here now. 5120 bytes. So that's the free space that I can use for my sprites. Alright, so how many bytes does one sprite graphic take? That's 64 bytes. So if I divide this number by 64 bytes, I'm gonna find out how many sprite graphics I can have. So I'm gonna divide this by 64 bytes. And I end up with this number, 80 sprite graphics. That's how many sprite graphics I can cram in from 2400, my starting area for my sprites, all the way up to 3800, where the character set begins. So I can fit 80 sprite graphics in there. Alright, now I think we looked at this last time, but if I'm going to start my character set at address 3800 and one character set takes up 800 in hexadecimal. So I think we looked at that last time and saw that we ended up at address 4000. So already I've started to fill up a lot of stuff. Although I haven't really done it, I'm just planning it in my head. But from 1000 here I have music, then somewhere around here after 2000, 2400 I think it was. From here we're starting to fill in sprites to somewhere around here, 3800, that's the character set, so we're going to fill in that here. So from address 4000, I'm actually going to dedicate this entire area from 4000 to 5000. I'm going to dedicate that area just for tables. Only going to use that area for tables. So, of course, planning stuff like this, let's be honest, it takes a little experience. You need to do some trial and error and do some math here and there. So I've done this a few times, so it's not too hard for me to know how much space the different things take. But I know that I'm going to be using a lot of tables. And tables can quickly take up space, especially long tables. Because a table, that's just a lot of bytes, right? So the longer the table is, the more space it's going to take. So 1000 in hexadecimal. So from 4000 to 5000. 1000 in hexadecimal, that's 4. Okay, let me show you. So hexadecimal 1000, which is all the space in here. That's 4096 in normal decimal. So in other words, 4 kilobytes. So I'm going to use 4 kilobytes only for tables. It's this area right here. And from memory address 5000, that's where I'm going to start with my main code. That's all the logic that I'm going to the heavy lifting of the programming. So there's going to be a ton of code in from memory address 5000. So it can be hard to say exactly how much space you need for your code. So we're at least going to use these two. So 8 kilobytes. Now this is for this specific project. This is going to be different from every project, of course. How much space do you need for code? How much space do you need for sprites, music, whatever. So it's going to be different. But the main point I'm trying to make here is that we need to plan ahead. Especially if you're starting a big project or starting to make a serious game or whatever. We need to do this kind of planning, because if we don't, it's going to just be a complete chaos. And we are not going to know where things are, how much space they take up, and so on. So we need to plan these things in detail. Now, the last thing in our code, in our game, is going to take up a ton of space, is our levels. So what we looked at last time. So you remember when we were drawing the level with the tiles. So the level graphic. That, let me just show you on my calculator. That was actually 16 tiles across, 12 tiles down. So that means that one level, one screen, or one room, as I'm going to call it, one room is going to take up, if we take 16 tiles wide times 12 times tall, it's 192. Now, once again, I've done a little math here, and I know that if I do, let's imagine we are in Charpad, and we set up Charpad in such a way that we have 8 rooms by 8 rooms, so 64 rooms in total. If we do it that way, 64 rooms. So if this is how much space one room takes up, I need to multiply that by 64. So I'm going to say 192 times 64. This is how much space all of my rooms is going to take up. So you remember the big file we exported from Charpad. When we start making a game, this is the size that's going to be. So it's around, let's say, maybe 12 kilobytes. And in hexadecimal, that's 3000. Which means I'm going to cram my level data, or my my rooms. I'm going to start here at address 7000. So 1000, 2000, 3000. Which means that now we have used up pretty much our whole area here. Except, of course, this code area. Because we can do most of this stuff at the very beginning of our project. If we have our music, if we have our sprites, if we have our character set, if we have our room graphics, then we can cram those in those specified places. But only when we're done programming do we know how much our actual code is going to take up. But from experience, I know that 8 kilobyte should be sufficient for us in this case. Alright, so there's a lot of stuff to keep track of here. So let's take a look at something more concrete. How are we actually going to do this? Let's look at the files I exported last time. Now, let's not focus on this Charpad file itself, because as we remember, that's just a project file. That has nothing to do with our code. In fact, let me make a separate folder for that. I'm just gonna call my folder Charpad files. And I'm going to drag that file in there. So now that's out of the way. Now the other 4 files, those are binary files. So those are the files that I need to use in my code. My character set attributes, my tileset, and my rooms file. So these 4 files, how can I get them into my code? Actually, we have seen this before, but let me just start by saying basic upstart to main, like that. So the normal way. Yeah, for now this is just an example, so let me just say game loop down here, jump to game loop, like that. So I'm going to save that file as main.asm. So this is nothing new. This is something we've seen before. Just creating a simple main file with this game loop like this. Now we're going to look at something new. So we spent all this time talking about planning of memory usage. How are we going to solve that in code? Well, we're going to create a new file. So I'm going to make a new file here. And I'm going to, this is something that I'm going to do in the future when we start writing serious code. So you already know about this double slashes like that, and that just creates a comment. So whatever comes after these 2 slashes is not really a part of the code. So I'm going to do this tidy, and just like a heading at the top of the file, I'm going to say what that file is. Right now we're going to make something called a memory map. So I'm going to say memory map here at the top. And, just to make it a little tidy, I'm going to do it like that. So now I'm going to save my memory map file. Just going to save it here together with the main file. I'm just going to call it memory map.asm, like that. So I'm going to have a separate file just to keep track of where things are going to be in my memory. Now we are going to see a few things here that we haven't covered yet, so let's not worry about the details there. But how are we going to do this? Let me also just mention something. Now I noticed in an episode just a few episodes ago, I said that this was a label. Yes, it is. We can even see the word label here. But in the previous episode, I used another word. I used the word constant for this. So this is a little confusing. Let's just get this out of the way right now. So in Kick Assembler, you can make constants 2 different ways. You can do it this way, like we already have done, but there's also a function, there's also something called .const. Like that. Right, fine, whatever. There we go. So there's actually something called .const for making constants. Now the reason I'm not using this to create constants is because it's gonna make our lives tiny little bit harder, because you need to be aware of how you're using the constant. Now for this label thing, we don't have to worry at all. We can just specify a label pretty much wherever we want, and then we can just use it in the rest of our code. Now for this .const, you have to think a little bit about more about what you're doing. So we're not going to be using .const, even though it's made for making constants. So let's not use .const, because this is going to give us pretty much the same result without the problems. It's not a huge issue, but this is one less thing to think about. So this is going to make perfect constants for us. Dot label a name like this, an equal sign, and a number. It's going to make a perfect constant for us. No problem. And by the way, I think we've seen this before, but let's just once again drive home the point. So constant like this could be a number like 45. It could also be a memory address like 2045. So it's just a constant here. It's just to specify some kind of number that makes sense to us, whether it's a memory address or any other kind of number. All right, just to be absolutely sure that we know what we're doing. So my memory map here is actually just going to be a list of these constants like that. Constants, label, whatever you want to call it. The point is that these are not going to change, so they are going to be constant. Now, like I said, we haven't talked about this, but for now, let's just try to accept it and remember that I'm going to cover that in a future episode. But the very first thing in my memory map is going to be something called 0 page. So for every entry here in my memory map, I'm going to say at the end here, address. So that's going to be, let me just write my equal sign here. And for this case, I'm going to write the address 20 here. So I'm going to write the word address here. And that's going to tell me that whatever this memory address is, that's the starting address for what I specify here. So in broad terms, I'm making a list, I'm making a plan where I'm going to cram in my things. And every one of those things is going to have a label like this. So let me just continue on here. I'm going to write label. I'm actually, right, at least for now, I'm going to call my thing game code here. Maybe I should use the word address too, since I made such a big deal about it. So game code address. That's going to be my main file. So the absolute main file where we have our basic upstart and our main code. So the absolute beginning. No, I'm sorry, that was not right. Oh my god. The main file is not a part of my memory map. I'm sorry about that. Okay, let's do this for real, so I don't get confused, so I don't confuse myself. Let me make one more file here. I'm gonna make a new file. I'm sorry that this was a little confusing. So this file is something I'm going to call, let me just copy this thing. So this is something I'm going to call game code. So this game code thing is going to be what I usually have here under basic upstart 2. So in other words, I don't have a lot here right now, but I'm going to take whatever I have right now, including my main label. So I'm just going to select everything there, and I'm going to cut it from here. and then I'm gonna go back to my game code, and I'm going to paste it in here. Now I'm going to save my game code file, and I'm going to call it gamecode.asm. So what on earth is going on right now? Well, so I want to utilize as much as I can of the Commodore 64 memory. And like I said, I want to do it tidy. I want to specify where everything is in code. Now, we know that this basic upstart thing, main, that's just this basic command, and it starts. It just starts a machine language program. So it starts our assembly code starting at the specified address. I'm going to say here in my memory map, my game code address is going to start at 0810. So, again, just to be sure that we don't get confused about this, 0810. Well, let's remember this. We start our entire thing here at 0801. This other thing are at the start of our assembly code and all that. That's going to be at 0810, because we already looked at this before. But our little line of basic code, that also takes up space. So that's why we end up at this memory address instead. So the very start of the basic memory area, but then we have our little line of basic code. So this is the actual start of our code, 0810. All right, so let's go back here. So that's going to be a game code address. That's where I'm going to cram in all of this stuff. So don't worry, I'm gonna connect the pieces eventually here. But let's just continue with this memory map. So hopefully you're starting to see a pattern. I write what it is that I want to cram into the memory, and I write a memory address. Now for this case it's not so apparent, we haven't talked about zero page, but for this example maybe a little bit more. And now I'm going to make another one. I'm going to call this variables address. So I want to have to separate my variables so that I know where my variables are, and I want to keep track of as many things as I can, so that I don't have data colliding with another data in the memory. Yes, I just want to make this whole thing tidy. So variables address. How much space do I need for variables? Okay, so I need to remember that one variable, that's 1 byte. All right, now once again, this has to do with experience, how many times you've done this, trial and error, and so on. So, and of course, it's going to vary from project to project. But in this case, I think we'll say that let's be generous and say that we can have 256 variables in our game. I think that's going to be enough. So if we say 256, that's 100 in hexadecimal. So now the big question comes. this was game code address. So game code is going to be this thing. So my game loop and all that stuff. Now, how much space is this going to take? Once again, we only have to base this on experience, trial and error, stuff like that. Now, I'm going to say that this is probably going to take up at least 512 bytes. So if I say 512, what's that in hexadecimal? So that's 200. All right. Let's go back to my here. Actually 512, that's not a lot. So what if I say 1024, so 1 kilobyte? There's a chance that my main code here could be 1 kilobyte. Now this is going to be a little hard because we haven't really talked about this, but I'm going to split up the code quite a bit. And if you remember when we looked at the Excel sheet, I talked about some kind of main code from address 5000. That's going to be something that I call libraries. That's going to be my main code. This code is just going to be some kind of code to connect these things together. Right, let's not get buried in details here. The point is that I need to find out where should I start putting my variables. How can I find out where to do that? So now I just said this game code area. Let's just say 1 kilobyte. That should be decent for this code area, this game code area. So 1024, that's 400 in hexadecimal. Okay, so what if I now say, what's this? This is the start of the game code address, all right? And this is 1 kilobyte in hexadecimal. Fine. 810 plus 400. That's 0C10. Okay, so we don't have to be super specific here. I just more or less guessed 1 kilobyte for this game code. So I think it's going to be fine if we just adjust that number down a little bit, but just a few bytes. So by doing that, we can get a cleaner address. So instead of 0C10, I'm going to say 0C100. That's where I'm going to place my variables, which means that now I should have a decent amount of space for my game code. You know, the game code, game code that's going to combine these things, my game loop and all that stuff. So this is not going to be the main code, I'm sorry, there are a ton of words here, things can get confusing, I'm sorry about that. But this code with our main and our game loop, this thing is going to connect a lot of our code. So that's going to have almost a full kilobyte, and that's going to be plenty space. I'm going to start my variables here at address C100, 0C00. Now, just a few minutes ago, I found out that I'm going to use 256 bytes for variables, which means we can have 256 variables. I also found out that, let me just write C100. Now I also found out, like I said, that I want to have 256 variables. That's 100 in hexadecimal. So 256 in decimal, that's 100 in hexadecimal. So what if I add 100 in hexadecimal, 256? I end up with D100. So what's the next thing I need to add in my memory? Well, I'm actually going to cram in my tileset now. Oh, wait a second. How big is my tileset? Alright, so first of all, let's just make the label for that. Tileset address. And I just found out that it should be at D100. So 0D00. Now, how big is my tileset? Okay, so there's a lot to keep track of now, a lot of numbers, all that stuff. But if we remember from last time, I said our tileset, the number of tiles that we can use, not characters, but tiles. I said 64. We should have 64 tiles. I also said that each tile is going to take up 4 bytes of memory, because one tile is made up of 4 characters, and every one of those characters has a screen code. So let's imagine it was a tile made up of 4 A's. So we have screen code 1, 1, 1, 1. That's how the tile system works. Which means when I said 64 tiles, we need to multiply that by 4. Because we have 64 tiles, every tile takes up 4 bytes. So I'm going to multiply that by 4. And once again, I end up with 256. Which we just found out is 100 in hexadecimal. Alright, so whatever next comes after this, then that's going to be at address. Let me take this 0D100 and add. Just found out that the tileset is 100 in hexadecimal, so I'm going to add that. This is going to be the next address. So whatever I'm going to add in here is going to be that. Alright, now, do I have something else in here? I have this thing right here, the character set attributes, char set attrib. Now, if you don't remember what that was, let me quickly remind you. We exported the character set and the color information separately. Now we know that the character set is 2 kilobytes. We talked about that before. So a full character set is 2 kilobytes. How much is this character set attributes? Well, then we have to think about what is that actually? What are those attributes? So I said, right now, let's just think about that as the color information. Now we already know that setting a color on a character in the Commodore 64, that's just storing a number at a specified address in the memory. We have this color RAM, right? So storing a memory, storing a number, storing a color code in one of those memory addresses in the color RAM. So 1 byte for a screen, for a color code. So we have 1 byte for a color code. How many characters are there in a full character set? Well, there are 256 characters in total in a full character set. We have 256 characters. Now, if one color code is 1 byte, that makes it really simple. So after all that, the character set attributes is 256 bytes because it's just 1 byte for every character in the character set. So let's see if that's correct. Size 256 bytes. Yeah. So my character set also takes up 256 bytes. Now let me just write this label. And I'm going to say char set attrib address. And remember, this tile set was also 256 bytes. And we remember that we added that to this address. We ended up with E100. So I'm going to say 0E100. Now, for the last thing here, before my address 1000, I'm going to say, first of all, we just found out that the character set attributes was 256 bytes. Just found that out. We also know that that's 100 in hexadecimal. So let me just add that to this one right now. I'm going to add 100 because we know that this is 256 bytes, which leaves us at memory address 0f100. So let me just write that down. 0f100. That's going to be the next address. But what should I put in there? Alright, so what I have planned for this project is, I've talked about this HUD quite a lot. We're going to take a look at that, but not right now. So that's going to be the area at the right of our room, at the right of our screen. It's going to be a little area there, the area where the sprite can't move, right? We're going to use that area for our HUD. So we're going to display score, lives, power-ups, maps, whatever in there. So the way I'm going to draw that HUD is not by drawing tiles like we're going to do with our level, but I'm going to draw simple characters. So by doing that, so there's a ton of stuff to keep track of right now, but if we can imagine that free or that unused area to the right of our level, so let me bring up my calculator. We have 16 tiles that we looked at last time. Each of those tiles are 2 characters wide. So I'm going to multiply that by 2, which means that our screen, or our level, if you want to call it that, that's a level graphic. It's 32 characters wide. We have 16 tiles and each of those is 2 characters wide. So our level is 32 characters wide. Now, what's the total of the screen length in characters? That's 40 characters by default. So if we take that full length of characters, subtract 32, which was the level width in characters, we end up with 8 characters. So there are 8 characters way on the right that we are not using when designing a level. That's the area where the sprite can't move because it's so far to the right. 8 characters wide. So how tall was our level? That was 12 tiles tall. Every tile is 2 characters tall, which means 12 tiles times 2. 12 times 2, that's 24. So our HUD is going to be 24 characters tall is going to be 8 characters wide. That's the area all the way at the right of the screen, to the right of our level. So if I divide 24 characters tall, if I multiply that with 8 characters wide, I end up with 192. So there are 192 characters in that area. So we can make a fancy looking HUD there. We can basically do what we want there, but there are 192 characters in that area. That HUD area, I'm going to have to need to store that somewhere. Now this is really nice because we didn't go over 256, which means that this is going to work out great for our memory map here. So if I say HUD address here now, then we have something that starts at F100, and we know that our HUD graphic or our HUD area takes up 192 bytes. Now in hexadecimal, that's C0. So this would go from 0F00 to 0F C0. So not all the way to 0FFF, but that's fine. That's fine. So we know that there are a few bytes there at the end before we start at address 1000. Now this is a lot of information, so let's just continue on here, and then let's let everything sink in. All right. Anyway, we have the next thing now. This, let's say that this is going to take almost 256 bytes, so that we don't bother with anything else at the F100 range. So the next thing is going to be at address 1000. And I actually said before that I'm going to place my music there. So at address 1000, that's when I'm going to start cramming in music from. And if you remember from earlier in this episode, I talked about my sprites. Sprites, yeah, let me just call it sprites address. This is a sprite graphics. So I said that we found out that sprite graphics should start at address 2400 because of the size of our music file. So that means that my sprites are going to start at 2400. That's what we found out. We also found out we're going to use 80 sprites, and by doing the math we end up with another address. So that's going to be our character set, and the character set is going to be placed at address 3800. That's where we're going to cram in our character set. We also did a little planning here, so we know that we know how large our character set is, and we know the next address we need to use because of the size of the character set. So next address here is going to be 4000, and that's going to be my tables. So tables address, that's going to be at address 4000. And I also said that tables, I'm going to set aside 1 kilobyte for tables. 4 kilobytes for tables. So that's 1000 in hexadecimal. So I'm gonna say for the next thing that comes after tables, that's gonna be what I'm going to call libraries. So all the meat or the meat of our code, all the main logic of our code, that's going to be in something I'm going to call libraries. So libraries address is going to be at address 5000 because I've set aside 4 kilobytes for tables. So what comes after libraries? Well, I said that I'm going to set aside 8 kilobytes for the code library. 8 kilobytes. So if 4 kilobytes was 1000 in hexadecimal, then 8 kilobytes is going to be 2000. So I'm going to say label rooms address. That's going to be at address 7000. So by doing this, like I said, it's a ton of stuff to keep track of, ton of stuff to remember, but this is going to be our memory map. So by specifying what it is we want to cram into the memory, and specifying the starting address of that here, we basically have made some sort of structure for how we're going to use the RAM in a Commodore 64. So this is, like I said, it's a ton of stuff to remember, and to make a proper memory map, you're probably going to have to do some trial and error. Maybe you need some more experience, testing out things, doing some math, whatever. But once you start to see how these things connect, then it's going to be easier to make a memory map like this. But hopefully you see the point, you see why we're doing this. Because now we know exactly where the different things are. So for example, when it comes time for us to tell the Commodore 64 where the character set is, then it's no problem. We know exactly where the character set is. When we want to use a specific sprite graphic, again, no problem. We know exactly where that is. So, and obviously all the other stuff as well. So we know where everything is, and now it's going to be much easier for us to plan. How much space can I use for this? How much space can I use for that? And so on. All right. Well, I was thinking that we should include that we should do some more coding here, but I think this episode has run long enough, and I think we're going to do that in the next episode. So that's where we're actually going to cram the different things into the different memory addresses. But for now, I think it's a good idea if we just sit back and let it all sink in, and I'll see you next time. Bye bye.